And now in this lecture I will answer two questions. The first question, we find out the size of this angle x is actually angle AMQ that equals to x. We have to find out the value of angle x. And in the second question, we find out the area of this circle that is described by this trapezoid ABCD. So we start with the first question. In the drawing, we have a semicircle. Point O is the center of the semicircle. AB is the diameter of the semicircle. AB is the diameter. And we know that OS equals to SB. Inside this semicircle, we have this square PQSO. Again, our task is to find out the size of this angle AMQ is equals to x. We have to find out the value of angle x. So first of all, we know that all the angles inside any square are right angles. So those four angles are all right angles. So actually, this is a right angle. This is also a right angle. This is a right angle. And this is also a right angle. AB is the diameter of this semicircle. AB is the diameter, it is absolutely a straight line. So if you focus on the upper side of the straight line AB at point S, here the sum of the angles must be equal to 180 degrees according to rule 3. Rule 3 says that the sum of the angles on one side of a straight line is equal to 180 degrees. So which angles we have at the upper side of AB at point S? We have this angle that is a right angle, plus this missing angle. In total, the sum of those two angles must be equal to 180 degrees according to rule 3. Therefore, this missing angle must be equal to 90 degrees in its side. We also know that all the sides of any square are equal to each other. That is to say, side QS equals to side SO, and square PQSO. So SQ equals to OS. Again, SQ equals to OS. But it is given us the question that OS equals to SB. OS equals to SB. So for this equation, SQ equals to OS equals to SB, we derive that SQ equals to SB. SQ equals to SB. In the next step, we join points B and Q together by a straight line. And we will extend line segment BQ by a straight line until it touches the semicircle. We'll define the touching point of the extended straight line BQ with this semicircle. This point is point N. By doing this construction, we're going to do the right triangle QSB. In the right triangle QSB, in front of those two equal sides, we have those two angles that must be also equal to each other in their sizes, according to the rule that in front of equal sides in the triangle there are equal angles. So if we define the size of this angle as y, then the size of this angle must be also equal to y because they are equal to each other. We also know that the sum of the angles in any triangle is equal to 180 degrees. So which angles we have at the right triangle QSB? Y plus y is 2y plus 90 degrees. In total must be equal to 180 degrees. That is the sum of the angles in a triangle. So in the right triangle QSB, 2y plus 90 degrees must be equal to 180 degrees. Here we subtract 90 degrees from the equation, and we get that 2y equals to 180 degrees minus 90 degrees is 90 degrees. So 2y equals to 90 degrees. Here we divide this equation by 2 and finally get that the missing angle y is equal to 90 degrees over 2. 90 degrees over 2 is 45 degrees. So the missing angle y equals to 45 degrees in its size. This is the missing angle y that equals to 45 degrees in its size. And this is also angle y that equals to 45 degrees in its size. We actually joined points B and Q by a straight line, therefore BQ is a straight line. Then we extended the straight line BQ by a straight line. When we extend the straight line by a straight line, the result BN must be also a straight line. So BN is a straight line. If we focus on the left side of the straight line BN at point Q, here the sum of the angles must be equal to 180 degrees according to rule 3. Repeat again on rule 3. According to rule 3, the sum of the angles on one side of a straight line is equal to 180 degrees. In our case, it means that the sum of the angles of the left side of the straight line NB at point Q must be equal to 180 degrees. So we can guess we have at the left side of the straight line NB at point Q, we have this angle is equal to 45 degrees in its side. Plus this angle that is a right angle, it is one out of 4 angles of square ABCD, of square BQSB. It is equal to 90 degrees. Plus this missing angle, that is actually angle NQP. In total, the sum of those three angles must be equal to 180 degrees according to rule 3. Repeat again. On the left side of the straight line NB at point Q, the sum of the angles must be equal to 180 degrees according to rule 3. That is to say 45 degrees plus 90 degrees plus the missing angle in QP must be equal to 180 degrees. 45 degrees plus 90 degrees is 135 degrees. So 135 degrees plus the missing angle NQP. In total, they must be equal to 180 degrees according to rule 3. Here we'll subtract 135 degrees from this equation. And we'll get that the missing angle NQP, the size of the missing angle NQP is 45 degrees. This is angle NQP. That is equals to 45 degrees in its size. In the next step, we will join points M and N together by a straight line. And we will also join points N and N together by a straight line. By joining points M and N and A. But sometimes we're going to do peripheral angle AMN. This is peripheral angle AMN that subtend on chord AN. And again, this is peripheral angle AMN that subtend on chord AN. Likewise, we have also peripheral angle ABN that also subtend on the same chord called AN. And therefore, according to rule 16, we get that if two peripheral angles subtend on the same chord, two or more peripheral angles subtend on the same chord, then they are equal to each other in their sizes. Okay, click on rule 16. According to rule 16, peripheral angles that subtend on the same chord are equal to each other. So in the drawing, we have a circle. This is peripheral angle AOB that subtend on chord AB. Likewise, we have another peripheral angle ACB that subtend on the same chord called AB. And because of the fact that those two peripheral angles subtend on the same chord called AB, they must be equal to each other in their sizes. That is to say, angle AOB equals to angle ACB, or alpha equals to beta. So if two or more peripheral angles subtend on the same chord, then they are equal to each other in their sizes. So this is peripheral angle ABN. Peripheral angle ABN equals to 45 degrees and it subtend on chord AN. Likewise, this is peripheral angle AMN that subtend on the same chord called AN. And because of the fact that peripheral angle ABN equals to 45 degrees in size, therefore peripheral angle AMN that subtend on the same chord called AN must be also equal to 45 degrees in size according to rule 16. So peripheral angle AMN is equal to 45 degrees in its size according to rule 16. By doing this construction, actually can do peripheral angle A and B. This is peripheral angle A and B that subtend on AB, that is the diameter of this semicircle. And according to rule 7, any peripheral angle that subtend on the diameter of the circle or a semicircle must be equal to 90 degrees in its size. So repeat quickly rule 7. According to rule 7, if a peripheral angle subtend on the diameter of the circle, then it is equal to 90 degrees in its size. So in the drawing, we have a circle. This is peripheral angle ACB that subtend on chord AB, that is the diameter of the circle, and therefore, according to this rule 7, peripheral angle ACB must be equal to 90 degrees in its size. So we can definitely implement rule 7 in our drawing. In our drawing, this is peripheral angle A and B that subtend on AB, that is the diameter of this semicircle, and therefore, according to rule 7, peripheral angle A and B must be equal to 90 degrees in its size. That is to say, it is a right angle. So in the right triangle A and B, this is the right triangle A and B, this angle equals to 45 degrees, this angle equals to 90 degrees, and therefore this third missing angle must be equal to 45 degrees in its size, according to the rule that the sum of the angles in any triangle is equal to 180 degrees. So in the right triangle A and B, in front of those two equal angles, we have those two sides that must be also equal to each other and their lengths. That is to say, in the right triangle A and B, side NA is equal to side NB. And therefore, the right triangle A and B, it is also an isosceles triangle, because side N equals to side NB. So I write it down. Triangle A and B is an isosceles triangle. equals side A equals to side NB. In the associated triangle, triangle A and B, AB is the base of the associated triangle, triangle A and B. So AB is the base of the associated triangle, triangle A and B. But AB is also the diameter of the semicircle. Here, AB is the diameter of the semicircle. We know that the diameter of any circle or semicircle is twice as long as the radius. So if the radius of this semicircle equals 2r, it means that the diameter must be equal to 2r. So the diameter of AB equals to 2r. So here we can implement rule 24 in our drawing. So I pick quickly rule 24. According to rule 24, the perpendicular to the base of an associated triangle bisects the base. In the drawing, we have the associated triangle, triangle ABC. Triangle ABC is an associated triangle because side AB equals to side AC. So in this associated triangle, triangle ABC, BC is the base of the associated triangle, triangle ABC. According to this rule 24, the perpendicular AO to the base BC bisects the base BC. First of all, AO is a perpendicular, therefore this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. And according to this rule 24, the perpendicular AO to the base BC bisects the base BC. That is to say, it divides the base BC into two halves. Each half equals to BC over 2. So the first half BO equals to BC over 2, the second half also equals to BC over 2, and of course the first half BO equals to the second half OC. So we can actually implement rule 24 in our drawing. Because in our drawing, we have the associated triangle, triangle A and B. AB is the base of the associated triangle, triangle A and B. According to rule 24, the perpendicular from point N to the base AB bisects the base AB. That is to say, it divides the base AB into two halves. Each half must be equal to AB over 2. AB over 2 is 2r over 2 because AB equals to 2r. So AB over 2 is 2r over 2. 2r over 2 is r. So each half must be equal to r, that is the radius of this semicircle. So the first half is r, and the second half also is r, that is the radius of this semicircle. But the question here is where the perpendicular from point N will touch the base AB. Because of the fact that the perpendicular from point N bisects base AB, it means the perpendicular from point N must touch the base AB at its midpoint. What is the midpoint of AB? The midpoint of AB is the midpoint of the diameter, that is 2r. And we know that the midpoint of any diameter is on the center of the semicircle or a circle. Again, the midpoint of any diameter is at the center of the circle or semicircle. Therefore, the midpoint of the diameter AB is at point O according to what is given to the question. O is the center of the semicircle. Again, the midpoint of the diameter AB is at point O, that is the center of this semicircle. Therefore, the perpendicular from point N to the base AB touch the base AB at point O, that is the center of the semicircle. So we actually have according to rule 24, the perpendicular NO to the base AB bisects the base AB. That is to say, it divides the base AB into two halves. The first half is R because AB over 2 is R, it is 2R over 2 that is R, and the second half OB is also R. Because of the fact that NO is perpendicular to AB, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We also have the rule that says that corresponding angles between parallel lines are equal to each other. I'm very quick on the rule. The rule says that corresponding angles between parallel lines are equal to each other. Those two angles 1 and 2 are defined as corresponding angles and are located between the parallel lines line 1 and line 2. That is to say, line 1 is parallel to line 2. And because of the fact that those two corresponding angles are located between the parallel lines line 1 and line 2, they must be equal to each other on their sides. That is to say, angle 1 equals to angle 2. We can actually implement the rule in our drawing. When put in our drawing, we know that the opposite sides of a square are parallel to each other. So in square PQSO, side PQ is parallel to the opposite side OS. And according to the rule that I mentioned, those two corresponding angles that are located between the parallel lines PQ and OS must be equal to each other and their sizes. But the size of this angle is 90 degrees, and therefore the size of this angle must be also equal to 90 degrees, according to the rule that I mentioned, that corresponding angles between parallel lines are equal to each other. So we have here angle PMN is equal to 45 degrees in its side and it's subtend on the base PN. Likewise, we have angle NQP that is also equal to 45 degrees in its side and it's subtend on the same base NP. And because of the fact that those two angles that are equal to each other are subtend on the same base NP, it means that they are cyclic. That is to say, you can block those two angles inside a circle. Exactly according to rule 16, that peripheral angles that subtend on the same chord are equal to each other. This is peripheral angle NPQ. Is equals to 45 degrees in its size, and it's subtend on chord PN. Likewise, we have peripheral angle PMN is equals to 45 degrees in its size, and it's subtend on the same chord PN. And it is exactly according to rule 16. Those two peripheral angles subtend on the same chord PN, and therefore they are equal to each other in their sizes. Each of them is equal to 45 degrees and therefore they are equal to each other. Therefore, we can block those two angles inside a circle. So, in the next step, we'll prove that quadrilateral NMQP is a cyclic quadrilateral. And again, we prove that quadrilateral NMQP is a cyclic quadrilateral. That is to say, you can block this quadrilateral NMQP in a circle, or it can be inscribed by a circle. But what is the meaning of this sentence that a quadrilateral is inscribed by a circle? This is the red quadrilateral ABCD. The red quadrilateral ABCD is inscribed by this circle. Why? Because all of its four vertices lie on the circle. You see, all the four vertices lie on the circle. And the whole quadrilateral ABCD is inscribed by a circle. So if all the four vertices of a quadrilateral lie on a circle, then it means that it is blocked by this circle. It is inscribed by this circle. So we have to prove that quadrilateral NMQP is inscribed by a circle. It will be inscribed by a circle only and only if all the four vertices N, M, Q, and P lie on the circle that blocks this quadrilateral. So, in order to prove that this quadrilateral NMQP is inscribed by a circle, I copied triangle NQP in a new page. In triangle NQP, this is an angle NQP that equals to 45 degrees in its size. So this is angle NQP. There's a cubic here, and angle. This is angle NQP. It is also triangle NQP. There's a cubic from the original drawing. In triangle NQP, angle NQP equals to 45 degrees in its size. We have the rule that all the triangles are cyclic. All the triangles are cyclic, and therefore triangle NQP is a cyclic triangle. That is to say, we can inscribe this triangle NQP by this circle. So we block this triangle NQP by this circle. Consider all the three vertices NP and Q lie on this circle, and therefore triangle NQP is inscribed by this circle. According to the rule that all the triangles in the world are cyclic, we can definitely block this triangle NQP by this circle. Now we have here principal angle NQP. This is equals to 45 degrees in its size, and it's subtend on chord NP. Likewise, we have also peripheral angle NMP. This is also equals to 45 degrees in its size, and it's subtend on the same chord NP. So those two peripheral angles that are equal to each other and subtend, they are both subtend on chord NP. They are both lie on the circle itself. That is to say, the vertex Q is on the circle itself, and the vertex M is on the circle. But what happens if we are talking about triangles, about angles that their vertex are not lie on the circle itself? For example, if this is angle NLP, the vertex L of angle NLP is lie outside the circle, but it still subtend on chord NP. If you measure this angle by scale, you get that angle NLP is equal to 39 degrees in its size. So in general, you can say that all the angles that lie outside this circle and subtend on chord PN will be less than 45 degrees. Like this angle, that is equal to 39 degrees, that is less than 45 degrees. Likewise, we have, this is angle NOP, that also subtend on chord NP, but it is located inside the circle. And the size of angle NOP is 85 degrees. So you can say in general that all the angles that subtend on NP and lie inside this circle, they are greater than 45 degrees. Like this angle, this goes to 85 degrees. And therefore we can conclude from those two examples that only the angles that lie on the circle itself, only the angles that their vertices lie on the circle itself, and the subtend on chord NP will be equal to 45 degrees in their sizes, because all the angles that are located outside the circle and subtend on PN then will be less than 45 degrees, while all the angles that subtend on chord PN and they are located inside the circle, they will be greater than 45 degrees. So only the angles that lie on the circle itself, only the angles that their vertices lie on the circle itself, and they are also subtend on chord PN, will be equal to 45 degrees. And therefore, if we rotate angle Q and NQP around this circle without changing its size, that is 45 degrees, we get all the angles that are equal to 45 degrees, and they also subtend on chord NP. Because chord NP is not moving, it is the axis. We will only move the vertex Q along this circle. By doing this operation, we get that all the angles that are simultaneously subtend on chord NP, and they are equal to 45 degrees. Why they will be equal to 45 degrees? Because we rotate angle NQP around this circle without changing its size. So in this way, we get all the angles in the world that are equal to 45 degrees in their sizes, and they are still lie on chord NP. The other angles that are located outside this circle will be greater than 45 degrees. It will be less than 45 degrees, and all the angles that subtend on chord NP and are located inside this circle will be greater than 45 degrees. Therefore, only the angles that lie on the circle itself and the subtend on chord NP will be equal to 45 degrees in their sizes. So by rotating angle NQP around this circle before changing its size, we get all the angles that are equal to 45 degrees and they subtend on chord NP. One of the angles will be angle NMP. This is of course equal to 45 degrees in its size because we didn't change the size of the angle. This is 45 degrees and it subtends on chord NP. Chord NP is not moving, so we just move angle NQP with its vertex along this circle, around this circle. Therefore, we get angle NMP that is equal to 45 degrees in size and it subtends on chord NP. Angle NMP, angle NMP is this angle that is equal to 45 degrees and it subtends on chord NP. We actually have here angle NMP that is equal to 45 degrees in size and it subtends on chord NP. In the next step, we'll join points M and Q together by a straight line. By doing all those operations, we get the quadrilateral NMQP. Quadrilateral NMQP is inscribed by this circle. Why? Because of the fact that all of its four vertices, N, M, Q, and P, lie on this circle. So in this way, I actually proved that quadrilateral NMQP is a cyclic quadrilateral. Why? Because we block this quadrilateral by this circle. So I know that quadrilateral NMQP is a cyclic quadrilateral. Quadrilateral NMQP is a cyclic quadrilateral. That is to say, it can be inscribed by a circle, it can be blocked by a circle. So we can block this quadrilateral by a circle. So I actually block this quadrilateral NMQP by this side of the circle. Why the circle blocks this quadrilateral NMQP? Because of the fact that all the four vertices of quadrilateral NMQP lie on the red circle. You can see point N, point M, point Q, and point N, point M, point Q, and point P, they all lie on the circle itself. Therefore, quadrilateral NMQP is inscribed by this circle. Quadrilateral NMQP is blocked by this circle. So here you can implement the rule that says that the sum of the two opposite angles in a cyclic quadrilateral is equal to 180 degrees. Quadrilateral NMQP is a cyclic quadrilateral because we can block this quadrilateral by this red circle, and therefore the sum of those two opposite angles inside quadrilateral NMQP must be equal to 180 degrees. So this is angle NMQ plus this angle MPQ in total must be equal to 180 degrees according to the rule that I presented to you. repeat again. Because of the fact that quadrilateral NMQP is a cyclic quadrilateral, the sum of its two opposite angles must be equal to 180 degrees. So the sum of those two opposite angles in quadrilateral NMQP must be equal to 180 degrees. So this is again NPQ. This is the right angle. Plus the opposite angle NMQ. In total, they must be equal to 180 degrees according to the rule that I presented to you. The rule says that the opposite angles of a cyclic quadrilateral is equal to 180 degrees. Angle NQP, angle NPQ, angle NPQ, angle NPQ plus 90 degrees in its size, plus the opposite angle NMQ. The opposite angle NMQ in total equals to 45 degrees, 45 plus X degrees. X is the angle that we are looking for in this question. So in total, they must be equal to 180 degrees. "90 degrees plus 45 degrees is 135 degrees. So 135 degrees plus the missing angle X in total must be equal to 180 degrees. Here we subtract 135 degrees from this equation, and we get that the missing angle X is equal to 180 degrees plus 135 degrees is 45 degrees. Angle X that is equal to angle AMQ is equal to 45 degrees in X side. So angle AMQ is equal to X is equal to 45 degrees in its size. So we finish with the first question. In the next step, I'll present you the second question, and we solve the second question of this lecture. In the second question, our task is to find out the area of this circle that is described by trapezoid ABCD. First of all, what is a trapezoid? A trapezoid is a quadrilateral with one pair of parallel sides. Repeat again. Trapezoid is a quadrilateral with one pair of parallel sides. In quadrilateral ABCD, side DC is parallel to the opposite side AB, and therefore quadrilateral ABCD is defined as a trapezoid, because it has one pair of parallel sides. If we define the two parallel bases, that is to say DC and AB, are defined as the bases of this trapezoid ABCD. If we define the length of base DC as A and the length of base AB as B, that is to say AB equals to B units in its length according to our definition, then the area of this trapezoid ABCD will be equal to the sum of its two parallel bases, that is to say A plus B, times the height edge over 2. The height edge must create 90 degrees with its two parallel bases. Again, a trapezoid is a quadrilateral with one pair of parallel sides, and the area of any trapezoid equals to the sum of its two parallel bases. In this case, it is A plus B times the height edge over 2, and the height edge must create 90 degrees with its two parallel bases. So, in the drawing, we have a circle that is described by trapezoid ABCD. Those two angles are both right angles. In addition, note that the area of this trapezoid ABCD equals to 3 square units in its size. Here, the length of side AB of trapezoid ABCD is equal to 3 units. Again, our task is to find out the area of this circle that is described by trapezoid ABCD. So first of all, we define the relevant points to this question with letters. We define the center of this circle. This point is point O. Likewise, we define the point of tendency of tangent DC with this circle. This point is point E. We define the point of tendency of tangent DA with this circle. This point is point F. And finally, we define the point of tendency of tangent AB with this circle. This point is point G. We define the radius of this circle as x. In the next step, we join points O and G together by straight line. Point O is the center of the circle, point G is the point of the circle itself, therefore OG is the radius of the circle, is equal to x. So here we can implement rule 1 in our drawing. Repeat quickly on rule 1. According to rule 1, a tangent to a circle is perpendicular to the radius drawn to its point of tendency. In the drawing we have a circle. This is tangent AB, that is tangent to this circle is point M. In addition, we have the radius OM that is equal to R. The radius OM is drawn to point M, that is the point of tendency of tangent AB with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the radius MO. If AB is perpendicular to MO, it means that this angle equals to 90 degrees, this angle also equals to 90 degrees according to this rule, rule 1. So we can implement rule 1 in our drawing. Why? Because in our drawing we have the radius OG that is equals to x. The radius OG is drawn to point G, that is the point of tendency of tangent AB with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the radius GO. If AB is perpendicular to GO, it means that this angle equals to 90 degrees. And this angle also equals to 90 degrees according to rule 1. Likewise, we join points O and F together by straight line. OF is of course the radius of this circle, that is equals to x. And according to rule 1, this angle equals to 90 degrees. And this angle also equals to 90 degrees. We join points O and E together by straight line. O is of course the radius of this circle, is equals to x. And according to rule 1, this angle equals to 90 degrees. And this angle also equals to 90 degrees. So in the upper quadrilateral DEOF, we have 1, 2, 3 rectangles. The sum of 3 rectangles is equal to 270 degrees. 270 degrees plus the size of this 4 facing angle, in total it must be equal to 360 degrees. according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. And therefore this fourth missing angle must be equal to 90 degrees in its size. So in quadrilateral DEOF we have 4 right angles, and therefore according to rule 5, any quadrilateral that has 4 right angles must be at least a right angle for the square. So we relate to this quadrilateral DEOF as a right angle. But we also know that the opposite sides of right angle are equal to each other. So in right angle DEOF, side EO must be equal to side DF, the opposite side DF. But EO equals to X, therefore the opposite side DF must be also equal to X units in its length. Likewise, in the lower quadrilateral FOGA, we have 1, 2, 3 right angles. Therefore, this fourth missing angle must be equal to 90 degrees in its size. So in quadrilateral FOGA, we have 4 right angles, and therefore can relate to this quadrilateral FOGA as a rectangle. But we also know that the opposite sides of rectangle are equal to each other. So in the lower rectangle FOGA, side FA must be equal to the opposite side OG, but OG is X, therefore the opposite side FA must be also equal to X units in its length. So side DA in total equals to X plus X, that is 2X. DA is the side of the trapezoid, it is absolutely a straight line. So DA equals to 2X units in its length. In the next step, we define the length of side DC of trapezoid ABCD as A. Side AB equals to 3 units in its length, according to what is given as the question. AB equals to 3. CB is the missing side, so we'll leave it as it is. We already proved that in the previous lecture that DA plus CB equals to DC plus AB. Again, DA plus the opposite side CB equals to DC plus AB according to rule 2. So I'll not repeat on the same proof again. So in trapezoid ABCD, side DA plus the opposite side CB is equal to side DC plus the opposite side AB. And then again, according to rule 2, we prove that actually it is so in any trapezoid that DA plus CB equals to DC plus AB according to rule 2. DA equals to 2X plus CB. CB is the missing side, so we'll leave this it is. And it is equals to DC. DC equals to A according to our definition, plus AB. AB equals to 3 units in its length according to what is given us the question. So in total, if we found out that (2x plus CB equals to A plus 3). Here we subtract 2x from this equation, And we get that the missing side CB equals to A plus 3 minus 2x units in its length. So actually, this is the missing side CB. It's over ABCD. Is equals to A plus 3 minus 2x units in its length. In the next step, we will do a construction. That is to say, from point C, we will draw perpendicular on AB. So actually, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point C and AB. This point is point M. By doing this construction, we can do quadrangle DCMA. Inside this big quadrangle DCMA, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees, so 270 degrees plus the size of this fourth missing angle. In total, they must be equal to 360 degrees. According to the rule that the sum of the angles in any quadrangle is equal to 360 degrees. And therefore, this fourth missing angle must be equal to 90 degrees in its size. So in quadrangle DCMA, we have 4 right angles, and therefore can relate to quadrangle DCMA is a rectangle. But we also know that the opposite sides of a rectangle are equal to each other. So in the bigger rectangle DCMA, side DC must be equal to the opposite side AM. But DC equals to A, therefore the opposite side AM must be also equal to A units in its length. Likewise, according to the sum rule, in the sum of the DCMA, side DA must be equal to the opposite side CM. But DA equals to 2x, therefore the opposite side CM must be also equal to 2x units in its length. What is the length of this missing 970 MB? MB equals to AB minus AM. So you know, MB equals to AB minus AM. So MB equals to AB. AB is 3, according to what this answer the question, minus AM. Just like no found out that AM equals to A. So total MB equals to 3 minus A units in its length. MB equals to 3 minus A units in its length. In the next step, I'll copy the right angle CMB in a new page, and we will implement on this right angle CMB the Pythagoras theorem. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. Here by PT is the evaluation for Pythagoras theorem. So here, this is our triangle CMB that comes from the original drawing. CM equals to 2x, therefore no CB equals to A plus 3 minus 2x, and MB equals to 3 minus A. In this right triangle CMB, according to the Pythagoras theorem, CB squared, that is the square of the hypotenuse, equals to CM squared plus MB squared. So write it down. CB squared, that is the square of the hypotenuse, equals to CM squared plus MB squared. CB equals to A plus 3 minus 2x, therefore CB squared equals to A plus 3 minus 2x squared. And it is equals to CM squared. CM is 2x, therefore CM squared is 2x squared. 2x squared is 4x squared plus MB squared. MB is 3 minus A, therefore MB squared is 3 minus A squared. And today we should know that A plus 3 minus 2x squared equals to 4x squared plus 3 minus A squared. Here we'll open the brackets on both sides of this equation according to the algebraic identity that A minus B squared equals to A squared plus B squared minus 2 times A times B. So A plus 3 minus 2x squared will be equal to A plus 3 squared plus 2x squared. 2x squared is 4x squared minus 2 times A plus 3 times 2x. And it is equals to 4x squared plus 3 minus A squared. 3 minus A squared equals to 3 squared, that is 9, plus A squared, plus 2 times 3 times A, that is minus 6A. Here we'll open the brackets of this expression and get that A plus 3 squared equals to A squared plus 3 squared, that is 9, plus 2 times A times 3, that is 6A. And here also, here 4x squared plus 4x squared minus 2 times 2x is minus 4x. So total, this expression equals to minus 4x times A plus 3. And it is equals to 4x squared plus 9 plus A squared minus 6A. So here we have A squared on both sides of this equation, so A squared will get cancelled. We have 9 on both sides of this equation, so 9 also will get cancelled. And we have 4x squared on both sides of this equation, so 4x squared also will get cancelled. After I cancelled all those expressions, in this side of the equation we left only with 6a. With 6a minus 4x times a plus 3, while on the other side of the equation we left only with minus 6a. Here we will get 6a and also minus 4 and also 4x times a plus 3 simultaneously to this equation. And we get that 6a plus 6a is 12a. 4x squared, 4x times a plus 3 minus 4x times a plus 3 is 0. And this is equal to 6a plus 6a is 0. And 4 plus 4x squared times plus 4x times a plus 3. Here we divide this equation by 4, and we get that 12a over 4 is 3a, so 3a equals to 4x over 4 is x, so in total this expression equals to x times a plus 3. So in total we found out that 3a equals to x times a plus 3. Here we divide this equation by a plus 3, and we get that x equals to 3a over a plus 3. And again, I found out that x equals to 3a over a plus 3. In the next step, we calculate the area of this trapezoid ABCD according to the formula that I presented to you at the beginning of the lecture. The area of trapezoid ABCD is equal to the sum of its two parallel bases, that is to say DC plus AB, DC plus AB, times the height. The height is cm because it creates 90 degrees with the two parallel bases, so times the height cm over 2. And again, if you found out that the area of trapezoid ABCD is equal to the sum of its two parallel bases, that is to say DC plus AB times the height cm over 2. DC equals to A, according to our definition, plus AB. AB is 3 according to what is given us the question, times the height cm. Cm is 2x over 2. So in total, if you found out that the area of trapezoid ABCD equals to a plus 3 times 2x over 2. We have 2 in the numerator, 2 in the denominator, so 2 gets cancelled. We left only with a plus 3 times x. So in total, if you found out that the area of trapezoid ABCD is equal to a plus 3 times x square units in its size. But according to what is given as the question, the area of trapezoid ABCD is equal to 3 square units. So we can substitute the area of trapezoid ABCD by 3 square units. We do it now, we get that 3 equals to a plus 3 times x. Yeah, if you found out that 3 equals to a plus 3 times x. But we already found out that x equals to 3a over a plus 3. X equals to 3a over a plus 3. So I can substitute x in this equation by 3a over a plus 3. We do it now, we get that 3 equals to a plus 3 times x, and x equals to 3a over a plus 3. We have a plus 3 in the numerator, a plus 3 in the denominator, so a plus 3 gets cancelled. And we're left only with 3 equals to 3a. Here we divide this equation by 3 and you get that a equals to 3 over 3, this is 1. A equals to 1. So we have the equation that said that x equals to 3a over a plus 1, and just line down found out that a equals to 1. So we can solve this equation by 1, and we do it now, we get that a equals to 3a. 3a is 3 times 1, that is 3, over a plus 3. A is 1, so a plus, again, x equals to 3a over a plus 3. So a is 1, so a plus 3 is 1 plus 3, that is 4. So today we found out that x, that is the radius of the circle, is equal to 3/4 units in its length. Our task is to find out the area of this circle that is described by trapezoid ABCD. Actually, you know that the area of any circle equals to pi times the radius of the circle squared. I repeat again, the area of any circle equals to pi times the radius of the circle squared, and therefore the area of our circle must be equal to pi times the radius of our circle squared. The radius of our circle squared is x squared, so total the area of our circle must be equal to pi x squared. So it is pi times x squared. X is 3/4, therefore x squared is 3/4 squared. 3/4 squared is 3 squared, that is 9, over 4 squared, that is 16. So today we found out that the area that we're looking for in this question, that is the area of this circle, is equal to either 9 pi over 16 square units in its size, or in terms of numbers, the area of this circle is equal to 1.767 square units in its size. And again, we found out that the area that we are looking for in this question, that is the area of this circle, it is equal to either 9 pi over 16 square units in its size, or in terms of numbers, the area of this circle equals to 1.767 square units in its size. So we finish with the second question. In the next step, I'll start with the lecture. We'll start with the first question, of course. In the first question, our test is to find out the size of this angle x that is equal also to angle A and Q. We have to find out the value of angle x that is equal also to angle A and Q. So in the drawing we have a semicircle point O is the center of the semicircle, AB is the diameter of the semicircle. In addition, inside this semicircle we have square PQSO, and we also know that OS equals to SB. Again, our task is to find out the size of this angle AMQ is equals to x. We have to find out the value of angle x. So first of all, we know that all the angles inside any square are right angles. So those four angles in square PQSO are all right angles. AB is the diameter of this semicircle, so AB is the diameter, it is absolutely a straight line. So if you focus on the upper side of the straight line AB at point S, here the sum of the angles must be equal to 180 degrees according to rule 3. Rule 3 says that the sum of the angles on one side of a straight line is equal to 180 degrees. So which angles we have at the upper side of AB at point S? We have this angle that is right angle plus this missing angle. In total, the sum of those two angles must be equal to 180 degrees according to rule 3. Therefore, this missing angle must be equal to 90 degrees in its size. We also know that all the sides of any square are equal to each other. So in square PQSO, side QS must side QS equals to side SO. QS equals to SO, but it is also given us a question that OS equals to SB. OS equals to SB, so for this equation SQ equals to OS equals to SB, we derive that SQ equals to SB. SQ equals to SB. In the next step, we did the construction, that is to say, we join points B and Q together by a straight line, and then we extended the straight line BQ by a straight line until it touches the circle. We define the touching point of the extended line segment BQ with this circle. This point is point N. By doing this construction, we're going to do the right triangle QSB. The right triangle QSB, in front of those two equal sides, we have those two angles that must be also equal to each other and their sizes, according to the rule that in front of equal sides in the triangle there are equal angles. So if we define the size of this angle as y, then the size of this angle must be also equal to y because they are equal to each other. In the right triangle QSB, the sum of the angles must be equal to 180 degrees. So which angles we have in the right triangle QSB? We have y plus 90 degrees. In total, they must be equal to 180 degrees according to the rule that the sum of the angles in any triangle is equal to 180 degrees. And again, in the right triangle QSB, according to the rule that the sum of the angles in any triangle is equal to 180 degrees, we get that 2y plus 90 degrees equals to 180 degrees. Here we subtracted 90 degrees from the equation, and finally found out that 2y equals to 180 degrees minus 90 degrees is 90 degrees, so 2y equals to 90 degrees. Here we divided the equation by 2 and finally found out that the missing angle y equals to 90 degrees over 2 is 45 degrees. So this is the missing angle y, this is equals to 45 degrees inside, and this is also the missing angle y, this is equals to 45 degrees inside. We joined points B and Q by straight line, and then we extended the straight line BQ by straight line. When we extend the straight line by straight line, the result Bn must be also a straight line. So Bn is a straight line, so if we focus on the left side of the straight line, Bn is point Q. Here the sum of the angles must be equal to 180 degrees according to rule 3. So which angles we have at the left side of BQ at point, the left side, which angles we have in the left side of the straight line and B at point Q, we have this angle that is 45 degrees, plus this angle that is 90 degrees, plus this missing angle MQP. In total must be equal to 180 degrees according to rule 3. And again, in the left side of the straight line and B at point Q, the sum of the angles must be equal to 180 degrees according to rule 3. So in the left side of the straight line BN at point Q, we have 45, one angle that equals to 45 degrees inside. The other angle is a right angle plus the missing angle MQP. Total must be equal to 180 degrees according to rule 2. 45 degrees plus 90 degrees is 135 degrees. So 135 degrees plus the size of the missing angle MQP. Total must be equal to 180 degrees. Here we subtract 135 degrees from this equation, and finally found out that the missing angle MQP equals to 180 degrees minus 135 degrees is 45 degrees. So this is the missing angle and QP, that is equals to 45 degrees in its sides. The next step is join points M and N together by straight line, and also join points N and A together by straight line. So here we have peripheral angle AMN. This is peripheral angle AMN. That's obtained or called NA. Likewise, we have peripheral angle ABN. Peripheral angle ABN also subtend on the same chord called AN. And therefore, according to rule 16, if two or more peripheral angles subtend on the same chord, they are equal to each other. So those two peripheral angles that subtend on the same chord called AN must be equal to each other and their sizes. But the size of this angle is 45 degrees, and therefore the size of this angle must also equal to 45 degrees. Because it subtends on the same chord called AN. So, by doing all those constructions, we get the peripheral angle A and B. This is peripheral angle A and B. And peripheral angle A and B subtend on AB, that is the diameter of this semicircle. And you know that any peripheral angle that subtends on the diameter of the circle or semicircle must be equal to 90 degrees in its size. And therefore peripheral angle A and B that subtend on AB, that is the diameter of this semicircle, must be equal to 90 degrees in its size according to rule 7. So in the right angle A and B, this angle equals to 45 degrees, this angle equals to 90 degrees, and therefore this first angle must be equal to 45 degrees in its size according to the rule that the sum of the angles in any triangle is equal to 180 degrees. So in the right triangle A and B, in front of those two equal angles, we have those two sides that must be also equal to each other and their lengths, according to the rule that in front of equal angles in the triangle, there are equal sides. So in the right triangle A and B, side A equals to side A equals to side A and B. Therefore, triangle A and B is also an isosceles triangle. Again, triangle A and B is simultaneously a right triangle and also an isosceles triangle. So here, know that AB is the base of the isosceles triangle triangle A and B, but AB is also the diameter of the semicircle. If the radius of this semicircle equals to r, then the diameter must be equal to 2r. So AB also equals to 2r because it is the diameter of the semicircle. So here we can implement rule 24 in the isosceles triangle triangle A and B. According to rule 24, the perpendicular to the base of an isosceles triangle bisect the base. The base of the triangle A and B is AB. So the perpendicular from point N to the base AB bisects the base AB. If it bisects the base AB, it means it divides the base AB into two halves. Each half must be equal to AB over 2. AB over 2 is 2R over 2 because AB equals to 2R. 2R over 2 is R. So the first half must be equal to R and the second half must be also equal to R. The question is where the perpendicular from point N will touch the base AB. AB is the base and it is also the diameter of the semicircle. So the perpendicular from point N bisects the base AB. If it bisects the base AB, it means that it must touch the base AB at its midpoint. The midpoint of AB is the midpoint of the diameter, and we know that the midpoint of any diameter is at the center of the circle or semicircle. Again, the midpoint of AB is the midpoint of the diameter AB, and that is at the center of the semicircle, that is point O. So the perpendicular from point N to the base AB will touch the base AB at point O, that is the center of this semicircle. So according to rule 24, the perpendicular NO bisects the base AB. Each half must be equal to R, and the perpendicular from point N will touch the base AB at point O. So it is a perpendicular NO, therefore this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We have the rule that corresponding angles between parallel lines are equal to each other. In square PQSO, the opposite sides are parallel to each other. So PQ is parallel to the opposite side OS. those two angles are defined as corresponding angles, and they are located between the parallels PQ and OS, and therefore they are equal to each other in their sizes. But the size of this angle is 90 degrees, and therefore the size of this angle must be also equal to 90 degrees, according to the rule that the corresponding angles between parallels are equal to each other. So those two angles, they are both equal to 45 degrees, and they subtend on the base PN. And therefore, those two angles are cyclic. That is to say, you can block those two angles by a circle. Why? Because they are equal to each other, and they are both subtend on the same base PN. This is the peripheral angle NQP. This is equals to 45 degrees inside, and it's subtend on chord PN. Likewise, this is peripheral angle NMP. It is also subtend on chord PN, and it is also equal to 45 degrees in size. And because of the fact that those two peripheral angles subtend on the same chord, they are equal to each other. Each of them equals to 45 degrees, therefore they are equal to each other. For that reason, you can block those two angles by a circle. It's exactly according to Rule 16 that says that peripheral angles that subtend on the same chord are equal to each other. For that reason, you can inscribe these two angles by a circle. So, in the next step, we prove that quadrilateral NMQP is a cyclic quadrilateral. What is the meaning of the sentence that a quadrilateral is a cyclic quadrilateral? It means that all the four vertices of the quadrilateral lie on the circle. This is quadrilateral ABCD that is inscribed by this circle. Why it is inscribed by this circle? Because of the fact that all the four vertices A, B, and C and D lie on this circle. So any quadrilateral that is inscribed by a circle means that all the four vertices of the quadrilateral lie on the circle. In the next step, we prove that quadrilateral NMQP is a cyclic quadrilateral. That is to say, we can put all the four vertices NMQP on a circle. Okay. In order to prove that quadrilateral NMQP is a cyclic quadrilateral, I copied triangle NQP to a new page. In triangle NQP, we have angle NQP that equals to 45 degrees in size. So actually, this is angle NQP, and it is also triangle NQP. So copy triangle NQP from the original drawing. And remember the rule that all the triangles are cyclic. That is to say, you can block all the triangles by circle. Therefore, we can definitely block this triangle NQP by circle. So we block this triangle NQP by this circle. You can see that all the three vertices N, P, and Q lie on the circle itself. Therefore, triangle NQP is inscribed by this circle. In the next step, we have here angle NQP. This is equal to 45 degrees inside, and it's subtend on chord NP. We have also angle PMN. That is also equal to 45 degrees inside, and it's subtend on the same chord called PN. What happens if we have an angle that is located outside this angle, like this angle? This is PLN, but it's subtend on the same chord called PN. What is the size of this angle? The size of this angle is 39 degrees. So you can say that all the angles that lie outside this circle and subtend on chord PN will be less than 45 degrees. Likewise, we have this angle that is angle PON, that is also subtend on chord PN, but the size of this angle is 85 degrees. So you can say in general that all the angles that lie inside this circle and subtend on the chord Pn simultaneously, they will be greater than 45 degrees. Like this angle is equal to 85 degrees. And therefore only the angles that lie on the circle itself will be equal to 45 degrees in its deal sizes. The lie on the circle itself and also subtend on chord Pn. Only those angles will be equal to 45 degrees in their sizes. The other angles that lie outside this circle will be less than 45 degrees, and all the angles that lie on the circle itself, they will be greater than 45 degrees. Therefore, if we rotate this triangle PQN around this circle without moving the excess Pn, and we keep the size of the angle without changing it, along this, if we rotate it along this circle, we get all the angles that subtend on chord Pn, and they are equal to 45 degrees. All the other angles that lie outside this circle will be less than 45 degrees, and all the angles that lie inside this circle and subtend on chord Pn will be greater than 45 degrees. So only the angles that lie on the circle itself will be equal to 45 degrees. In this way, by rotating the vertex Q around this circle without changing its size, that is 45 degrees, and Pn doesn't move, we get infinite angles that all of them lie on chord Pn, and all of them, each of them is equal to 45 degrees, because we will not change the size of the angle when we're moving it along the circle, around this circle. One of the angles will be angle NMP, that is also equal to 45 degrees in its size, and it subtends on chord NP. And this is angle NMP, that is equal to 45 degrees in its size, and it subtends on chord NP. In the next step, we'll join points M and Q together by straight line. By doing all those operations, we're going to do quadrilateral NMQP. This is the same quadrilateral NMQP. Together here. Quadrilateral NMQP. And quadrilateral NMQP it is definitely inscribed by this circle. Why? Because of the fact that all the four vertices of quadrilateral NMQP lie in the circle itself. Therefore, quadrilateral NMQP is blocked by this circle. Quadrilateral NMQP is inscribed by this circle. So you can find out that quadrilateral NMQP is a cyclic quadrilateral. Quadrilateral NMQP is a cyclic quadrilateral because of the fact that all the four vertices of quadrilateral NMQP that are NM, Q, and P, they lie on the circle itself. Therefore, it is inscribed by the circle. So, I block this quadrilateral NMQP by this red circle. Consider all the four vertices N, M, Q, and P lie on this red circle, and therefore quadrilateral NMQP is inscribed by this red circle. So here we have the rule that the sum of the two opposite angles of a cyclic quadrilateral is equal to 180 degrees. The sum of those two opposite angles of this cyclic quadrilateral NMQP is equal to 180 degrees. This is angle NPQ is equal to 90 degrees in size, plus the opposite angle NMQ, that is 45 degrees plus x. In total, the sum of those two opposite angles must be equal to 180 degrees. Repeat again, in the quadrilateral NMQP, the sum of its two opposite angles must be equal to 180 degrees because it is a cyclic quadrilateral. So, angle NPQ plus the opposite angle NMQ, angle NPQ plus the opposite angle NMQ. In total, the sum of those two opposite angles must be equal to 180 degrees according to the rule that I presented to you. Angle NPQ is a right angle. Angle NMQ is equal to 45 degrees plus x. Then again, angle NPQ is a right angle, angle NMQ in total equals to 45 degrees plus x. In total, it must equal to 180 degrees. 90 degrees plus 45 degrees is 125 degrees. So 125 degrees plus the missing angle x in total must equal to 180 degrees according to the rule that I presented to you. Here we subtract 125 degrees from this equation and find that the missing angle x is equal to 180 degrees minus 125 degrees is 45 degrees. So the missing angle, that is the angle that we are looking for in this question, that is angle x, that is also defined as angle AMQ, is equal to 45 degrees in its size. So we finish with the first question. In the next step, I actually presented to you the second question and we solve the second question of this lecture. In the second question, our task is to find out the area of this circle that is described by trapezoid ABCD. So, first of all, what is a trapezoid? A trapezoid is a quadrilateral with one pair of equal sides. This is quadrilateral ABCD. In quadrilateral ABCD, side DC is parallel to the opposite side AB. And therefore, quadrilateral ABCD is defined as a trapezoid because it has one pair of parallel sides. If we define the two parallel bases, DC and AB are defined as the bases of the trapezoid. So if we define the base DC as A, that is to say the length of the base DC is A units, and the length of the base AB is B, then the area of this trapezoid ABCD will be equal to the sum of its two parallel bases, that is to say A plus B times the height edge over 2. The height edge must create 90 degrees with the two parallel bases. So in total, you can summarize and say that a trapezoid is a quadrilateral with one pair of parallel sides, and the area of any trapezoid equals to the sum of its two parallel bases. In this case, it is A plus B times the height edge over 2. The height edge must create 90 degrees with the two parallel bases. So in the drawing we have trapezoid ABCD that blocks this circle, or a circle is inscribed. The circle is inscribed by this trapezoid ABCD. In addition, you know that those two angles are both right angles, and you also know that side AB of trapezoid ABCD equals to 3 units in its length, and the area of this trapezoid ABCD is equal to 3 square units in its size. Again, our task is to find out the area of this circle that is inscribed by this trapezoid ABCD. So first of all, we define the relevant points to this question with letters. We define the center of this circle, this point is point O. We define the point of tendency of the DC of this circle, this point is point T. Likewise, we define the point of tendency of the DA with this circle, this point is point F, and finally we define the point of tendency of the AB with this circle, this point is point G. And we also define the radius of this circle as x. Radius equals to x according to our definition. In the next step, we join points O and G together by a straight line. Point O is the center of the circle, point G is the point of the circle itself. Therefore, OG is the radius of this circle, is equals to x. The radius OG is equals to x. The radius OG is drawn to point G, that is the point of tendency of tangent AB with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the radius GO according to rule 1. If tangent AB is perpendicular to the radius GO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. Likewise, we join points O and F together by a straight line. OF is of course the radius of this circle, that is equals to x, and according to rule 1, this angle equals to 90 degrees, and this angle also equals to 90 degrees. Likewise, we join points O and D together by a straight line. O is the radius of this circle, that is equals to x. And according to rule 1, this angle equals to 90 degrees, and this angle also equals to 90 degrees. So in the upper quadrilateral DEOF, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees, so 270 degrees plus the size of this 4 pieces angle, in total they must be equal to 360 degrees, according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. And therefore this 4 pieces angle must be equal to 90 degrees in its size. So the quadrilateral DEOF or F, we have 4 rectangles, therefore can relate to one another DE or F is a rectangle. But we also know that the opposite sides of a rectangle are equal to each other. So in this one rectangle DE or F, side EO must be equal to the opposite side DF. But EO is x, therefore the opposite side DF must be also equal to x units in its length. Likewise, in the lower quadrangle FOGA, we have 1, 2, 3 rectangles, and therefore this 4 missing angle equals to 90 degrees. So in quadrangle OFAG, we have 4 rectangles, therefore can relate to quadrangle OFAG is a rectangle. So we know that the opposite sides of a rectangle are equal to each other. So in rectangle OFAG, side OG equals to the opposite side FA, but OG is x, therefore the opposite side FA must be also equal to x units in its length. So the length of side DA of trapezoid ABCD is equal to x plus x, that is 2x. In the next step we define the length of side DC of trapezoid ABCD as A. AB equals to 3 according to what is given as the equation, and CB is the missing side. We only proved that the previous lecture that DA plus CB equals to DC plus AB according to Rule 2. Again, DA plus CB equals to DC plus AB. So again, we already proved that in the previous lecture that DA plus CB equals to DC plus AB according to Rule 2. DA is 2x plus CB is the missing side, so it is. And it is equals to DC, that is A, plus AB, that is 3. So in total, if you want to know that 2x plus CB equals to A plus 3. Here we subtract the 2x from this equation, and finally found out that the missing side CB equals to A plus 3 minus 2x units in its length. This is the missing side CB, that is equals to A plus 3 minus 2x units in its length. In the next step, we did the construction, that is to say from point C, we do perpendicular on AB. So this angle equals to 90 degrees, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point C and AB. This point is point M. By doing this construction, we will do quadrangle DCMA. Quadrangle DCMA, quadrangle DCMA, we have 1, 2, 3 rectangles. The sum of 3 rectangles is 270 degrees. So 270 degrees plus the size of this 4 pieces again, in total must be equal to 360 degrees according to the rule that the sum of the angles in any quadrangle is equal to 360 degrees. And therefore this 4 pieces again must be equal to 90 degrees in its size. So in quadrangle DCMA, we have 4 rectangles, and therefore can relate to quadrangle DCMA is a rectangle because it has 4 rectangles. But we also know that the opposite sides of a rectangle are equal to each other. So in the big rectangle DCMA, side DA must be equal to the opposite side CM. But DA is 2x, therefore the opposite side CM must be also equal to 2x units in its length. Likewise, according to the sum rule, the sum rectangle DCMA, DC must be equal to the opposite side AM. But DC is 8, therefore the opposite side AM must be also equal to A units in its length. MB equals to AB minus AM. So MB equals to AB, that is 3, minus AM, that is 8. So in total, MB equals to 3 minus units in its length. In the next step, I complete the right triangle CMB in a new page and implemented the Pythagoras theorem in this right triangle CMB. According to the Pythagoras theorem in a right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So actually, this is the right triangle CMB that is coming from the original drawing. In this right triangle CMB, CB squared, that is the square of the hypotenuse, equals to CM squared plus MB squared. CB is A plus 3 minus 2x, therefore CB squared is A plus 3 minus 2x squared, and it is equals to CM squared. CM is 2x, therefore CM squared is 2x squared. That is 4x squared, and it is equals to CM is 2x, therefore CM squared is 2x squared, plus MB squared. MB is 3 minus 8, therefore MB squared is 3 minus 8 squared. So total, I can find out that A plus 3 minus 2x squared equals to 4x squared plus 3 minus 8 squared. We open the brackets, both sides of this equation. According to the algebraic identity, that A minus B squared equals to A squared plus B squared minus 2 times A times B. So according to the algebraic identity that I mentioned, A minus 3 minus 2x squared equals to A minus A plus 3 minus 2x squared equals to A plus 3 squared minus 2x squared, that is 4x squared, minus 2 times A plus 3 times 2x. And it equals to 4x squared plus 3 minus A squared. 3 minus A squared equals to 3 squared, equals to 3 squared, that is 9, plus a squared minus 2 times 3 times 8, that is minus 6a. We open the brackets of this expression, and we found out that a plus 3 squared equals to a squared, plus 3 squared, that is 9, plus 2 times a times 3, plus exactly a plus 3 squared. A plus 3 squared equals to a squared, plus 3 squared, that is 9, plus 2 times a times 3, that is 6a. So total we found out that a squared plus 9 plus 6a plus 4x squared equals to 4x times a plus 3 minus 4x times a plus 3 equals to 4x squared plus 9 plus a squared minus 6a. We have a squared on both sides of this equation, so a squared gets cancelled. We have also 9 on both sides of this equation, so 9 also gets cancelled. And we have 4x squared on both sides of this equation, so 4x squared also gets cancelled. In this side of the equation, we left only with 6a minus 4x times a plus 3, while on the other side of this equation, we left only with minus 6a. Here we added 6a and also 4x times a plus 3 simultaneously to this equation, and finally found out that 6a plus 6a is 12a, 12a equals to 4x times a plus 3. Here we divided this equation by 4 and finally found out that 12a over 4 is 3a, 4x over 4 is x, so in total this expression equals to x times a plus 3. So if we found out that 3a equals to x times a plus 3, here we divided this equation by a plus 3 and finally found out that x equals to 3a over a plus 3. In the next step, we calculated the area of this trapezoid ABCD according to the formula that I presented to you at the beginning of the lecture. The area of this trapezoid ABCD will be equal to the sum of its two parallel bases, that is to say DC plus AB times the height CM over 2. Again, the area of trapezoid ABCD equals to the sum of its two parallel bases, that is actually DC plus AB times the height CM over 2. DC is A, AB is 3, and CM is 2x. And again, DC is A, AB is 3, and CM is 2x. Divided by 2. We have 2 denominator, the denominator, so 2 gets cancelled, and we have only with a plus 3 times x. So in total, we found out that the area of trapezoid ABCD equals to a plus 3 times x coordinates in its sides. But it is given us the question that the area of this trapezoid ABCD is equal to 3 square units in its size. So we can substitute the area of trapezoid ABCD by 3 square units. So 3 equals to a plus 3 times x. We already found out that x equals to 3a over a plus 3, so we can substitute x by 3a over a plus 3. We did it, and we found out that 3 equals to a plus 3 times x, and x equals to 3a over a plus 3. We have a plus 3 in the denominator and a plus 3 in the denominator, so a plus 3 gets cancelled, and we left only with 3 equals to 3a. 3 equals to 3a, here we divided the equation by 3 and found out that a equals to 3 over 3, that is 1. So a equals to 1 units in its length. And again, actually found out that a equals to 1 unit in its length, and we have already found out that x equals to 3a over a plus 3. Now we can substitute a in this equation by 1, because a equals to 1. We did it, and we found out that x equals to 3a. A is 1, so 3a is 3 times 1, that is 3, over a plus 1. A is 1, so a plus over a plus 3. A is 1, so a plus 3 is 1 plus 3, that is 4. So in total, we found out that the radius of the circle equals to 3/4 units in its length. Our task is to find out the area of this circle. Actually, we know that the area of any circle equals to pi times the radius of the circle squared. And therefore, the area of our circle must be equal to pi times the radius of our circle squared. The radius of our circle squared is x squared. So in total, the area of our circle must be equal to pi x squared. X is 3/4, therefore x squared is 3/4 squared. 3/4 squared is 3 squared, that is 9, over 4 squared, that is 16. So in total, if you found out the area that you're looking for in this question, that is the area of this circle, equals to either 9 pi over 16 square units in size. In terms of numbers, the area of this circle equals to 1.767 square units in size. Okay, thank you very much.